Now that we have element stiffness matrix generic form, and we can use that to write element stiffness matrix for any element type in 1D, 2D or 3D. So we will see the steps in solving linear FEA problem. Earlier we have discussed this. Now we will refine. So the step one is given structure. We will we will discretize the structure into number of elements. Next step is to write element stiffness matrix for each element. Then we perform assembly of elements and we get a global system of equations. We apply loads and boundary condition into this global system of equations, and the next step is to solve for unknown displacements. Once we have this primary solution, okay, we find then other derived quantities like strains and then stresses. So we find the stresses from using this equation or using this relation. We know the strain displacement relationship. It is strain vector is equal to B matrix and U vector. So this is our displacements. Okay. Once we get UE, we have B matrix for all the elements. So we can find the strains in all the elements. Okay. Then using these strains, okay, we can find the stresses. Using stress strain relationship matrix D, and we have seen what is D for 1D, 2D and 3D. So these are now steps, and let's talk about little bit about this one, okay, which is kind of recap. So we know the element stiffness matrix generic form. Okay, it is integration over volume B transpose D B dV. So now we have seen this. Now let's see the what are the steps within this step. So we will see the sub steps for this step number 2. And we have seen the first thing we do is we determine the shape functions. That means we assume the trial function, that is n. Then step 2, okay, n is basically function of coordinates, okay, x, y, z for 3D. Then we find B matrix for each element. So B matrix, okay, which is basically derivatives of shape functions. Then we get D matrix stress strain relationship matrix, okay, which is a stress strain relation. So if we see while deriving K matrix for each element, okay, we have these different terms D and B, okay, and we can use these B and D calculations, okay, again in our stress and strain calculation or in our post processing. Okay, so this the representing the element stiffness matrix in this component, okay, it is actually very efficient, okay, because we can use the same D and B for those elements again for calculating these derived quantities.